Hello everybody, this is video 1 about semi-confined flow. In a semi-confined aquifer, the aquifer is covered on top by a leaky layer or a layer of low permeability. And I've shown one here where we have an aquifer of thickness capital H, and it is covered on top by a leaky layer, a layer of low permeability shown here in orange, and which is often consists of clay or peat. The leaky layer is also called the semi-confining layer. So it's not impermeable, but it allows a small amount of water to flow through. The case I've shown here on the left side of the dam, here in the middle, we have a lake with a fixed water level, and on the right side of that dam we have a polder where the water level is fixed near the surface by ditches and drains. So what will happen is that the water level on the left side is larger, so water will leak from the lake into the aquifer through the leaky layer, then flow through the aquifer and get back out in the polder. Leak through the leaky layer again, and it will flow into the polder. And of course, if the same happens a little farther upstream of the dam, it will go through here and go to the other side. Now this is only one situation you could have for semi-confined flow. You're going to arrive general equations for the flow in the aquifer below the leaky layer. The first step in that is to try to derive an equation for flow through the leaky layer. Let me redraw the semi-confined aquifer. We have an impermeable base. We have a leaky layer above it. And above the leaky layer we have a fixed water level in blue, this fixed water level, and we call that fixed water level H star. Now if we now know what the head in the aquifer is at a certain point, we can calculate the flow through the leaky layer. If the head in the aquifer H is larger than the head above the leaky layer H star, then QZ through the leaky layer can be calculated with Darcy's law. Of course, that means we need to know the thickness of the leaky layer, HV, and the hydraulic conductivity of the layer, KV. The V stands for vertical. And we can write down Darcy's law for flow through the leaky layer. QZ is equal to the head in the aquifer minus the head above divided by the distance between them, HV, and then multiply that by KV, the hydraulic conductivity of the leaky layer. Now what is often done is that the KV term and the HV term are combined into a value called C, the resistance, such that the flux through, or the specific discharge through the leaky layer can be written as H minus H star divided by C. Where, like I said, C is called the resistance of the leaky layer. Resistance of leaky layer. And the equation for C is that C is equal to the thickness of the leaky layer divided by the vertical hydraulic conductivity of the leaky layer. And if we figure out then what the units are, the thickness has units meters, the hydraulic conductivity has units meters per day, so the meters cancel, and the units of the resistance of a leaky layer are in days. All right, we have QZ now. Now we need to derive a differential equation for the head in the aquifer. Let's try to do that. We have already derived previously a differential equation for the head in the aquifer if we have a constant infiltration rate, N. That looks something like this, where we have an aquifer and we have a recharge N on top. And we had derived that the second derivative of the head with respect to x squared, this is for a one-dimensional flow, right, is equal to minus n divided by k and h. And this is for confined flow. The difference now is that we don't have n going into the aquifer, we have qz going out of the aquifer. So the sign convention is just opposite. So we can also write this is equal to plus qz divided by kh. And we have an equation for qz, which is right here in the top right hand corner in green, and we can substitute that in. So we have the second derivative of h with respect to x squared is equal to qz h minus h star divided by c times k times h. And this is often written in a slightly different form. It's written as h minus h star divided by lambda squared, where lambda, the Greek letter lambda, is defined as the square root of k times h times c. Lambda, let's first look at what the units of lambda are. It's the square root of k, meters per day, times h, meters, times c, days. So the days cancel. And the units are the square root of meters squared is equal to meters. So the lambda factor has units of length. And lambda is called the leakage factor, or in Dutch, it's called the spreidingslengte. And it is a length, and it's a characteristic length of the system, as we will find out in the next part of the video.